Hello. In this video, we shall be discussing about a few relations or a few formulas we can obtain by using Biot-Savart's law associated with the magnetic effect of electric current. Now, as far as the Biot-Savart's law is concerned, we have the magnetic field at any point to be given as mu naught over 4 pi I times of dl crossed with R is the cross product of the dl current carrying element with the position vector, and that can be integrated over the given length, that over the modulus of R raised to the power 3. Now the cross product of dl and R determines the direction of the magnetic field. So for a straight conductor, when we are to determine the magnetic field intensity at a point, let us say lying to the right of it at a perpendicular distance of r, then if we are considering a finite length of it, then the angles come into picture, and in that case, suppose we have the angles associated with the uh, conductor with respect to the point being alpha 1 and alpha 2 respectively. Now in that case, what we obtain is the magnetic field intensity considering the magnitude only. Will be considering the direction later, but as far as the magnitude of the magnetic field is concerned, we have mu naught times of I over 4 pi, the distance being r, and then we have the sine of the first angle, the top angle, that is alpha 1, plus sine of alpha 2. And as far as the direction is concerned, we have the cross product of dl and r. The dl over here is taken along the direction of flow of current. So in that case, you have the cross product of the cross product from that direction over to that direction, and the cross product as far as the right hand thumb rule is concerned, or right hand screw rule is concerned, that goes into the plane. Taking this case into account, what we get is, if we are to determine the magnetic field at the center of a square, now I'm giving you a generalized formula for that. Now the square has the length of each side to be equal to, let us suppose in this case, be equal to A, and we have the current flowing in the clockwise sense and wish to determine the magnetic field at the center of this arrangement. Now the center has to lie at a perpendicular distance of A over 2, because it's going to be half the length where the diagonals will be bisecting each other. Now I'm naming this, so we have the segments or the vertices as A, B, C and D. We'll be considering the segments one by one to determine the magnetic field for each straight conductor, and then we'll be taking the vector sum of all those magnetic fields and obtain the net magnetic field at that central point. So the center here is at the point O. First up, we have the segment AB. So the magnetic field for the finite segment AB can be given by the relation where, first of all, we'll be considering the angles that we have with us. Now the angles, because the diagonals are the ones which will be bisecting, they bisect each other at 90 degrees. So if we are considering uh, the distance from the center or from the midpoint, then it will be again bisecting it at 45 degrees. So 90 has been bisected by 45 degrees each, and with those 45 degrees angles, alpha 1 and alpha 2 become equal to 45 degrees. So for BAB, what we have is the magnetic field intensity is mu naught over mu naught times of I over 4 pi. In this case, the distance is A over 2 because it's going to be at a distance of half the length of each side, as I've shown over here. And then we have sine of 45 degrees taken twice because they are going to add up. Sine 45 plus sine 45 is 2 times of sine 45, and so this will give us, will be giving the direction as well. So this is mu naught times of I. A 2 can get cancelled over here to give a 2, and another 2 can get cancelled over here with the 2 above, and so we have mu naught I times of pi a. Now sine 45 is 1 over root 2, so that stays. Now if you are going to take the cross product of the length which is lying along AB towards the position vector of the point at O, then the cross product would yield you, it'll be taken from AB lying along that direction to the point O which is lying along that direction. So it's going to be screwing down the driving down the screw. So as a result of that, this will be going into the plane. So this goes into the plane, and then you have the magnetic field for the segment BC. And similarly, we have the angles concerned, which will be the same, of course, because it's going to be uh, bisecting at right angles, and when we are considering the central distance, it's going to be a over 2, and the same case, but the only thing that we wish to know is the direction in this case, and the magnitude is going to be the same, of course, with the same dimensions involved, but the direction, let's see if it's anything different. Well, the L vector is going downward in this case, and the R vector towards the point is along that direction, as you can see. So if you are turning the screw from the first vector to the second vector, again it will be driving the screw into the plane. So right hand screw rule is going to give you the same result over here as well. In fact, if you check for each of those segments, each of those segments would yield you the same result. So what you are going to get for CD, for AD, that will be the same in each and every case, which is going to be mu naught over I times of pi a, 1 over root 2, and all going into the plane. Now finally, if we wish to determine the total magnetic field, so the net magnetic field at the center is going to be equal to a sum of all of these, because all of them are directed along the same direction, so we are going to add them vectorially, which would eventually lead to an algebraic addition considering the same direction. So finally, we have 4 times of the magnetic field due to each segment that would be apt in this case. So 4 over root 2 is going to give me 2 root 2. So this is 2 root 2 times mu naught I over pi a. And that's a generalized form. You plug in those dimensions that you have been provided, and you obtain the value. You plug in the value of current and the dimension provided, and you get the answer right away. One more thing that you can consider, you have certain types of questions which would be providing you with one of the parts of the square, and then you have to determine the magnetic field for that part. Let's see, let's assume that you have been provided with this much amount of the square, where the point is lying at the center, but the rest of the square is missing. As you can see, you could have constructed a square over here, but that remains absent. So this is only a segment of the square that has been considered, or you can say a quarter of that value. So you are missing rest of the three parts over here, here, and here. So that means you are going to determine the magnetic field for only one part of it, and that would yield 1/4 of this value that you have obtained over here. That is 2 root 2 times of mu naught I over pi a. And what would that yield? Well, 2 cancels with that. You have root 2. So you have 1 over root 2 times of mu naught I over pi a. That's going to be the value for part which is probably 1/4 of the entire square. So I'll leave you with a question for you to determine, and we'll try out the answer in the next video. Let's see if you can get that right. So in this question over here, we have a stair-like arrangement where the dimensions have been provided. As you can see here, it is 2 centimeters, and then this is the point O lying at the center of what would have been a square of side 4 centimeters each. So this is 4 centimeters, of course. These are complete sides. But the point O lies exactly off that broken square. And also it lies at the center of a square which would have been 2 centimeters with each side. That is the small step that you see of 1 centimeter each. So what you need to determine is the magnetic field at that point O. You need to, that is the almost the center of both those squares. So that is what you have to determine. You can send me your answers in case you have found them, and we'll try this one in the next video. Till then, thank you for watching.